The proposed subgraph network-based contrastive learning (SGNCL) framework introduces a novel approach to graph contrastive learning by integrating subgraph network generation into the GCL paradigm. SGNCL leverages the concept of subgraph networks to capture the interaction information between substructures hidden in the original graph through an edge-to-node transformation. This transformation preserves both topological and attribute features of the original graph, enhancing graph classification tasks. In contrast to traditional augmentation strategies such as node dropping, edge perturbation, and attribute masking, SGNCL considers the interaction correlations within local subgraphs. Inspired by line graph theory, the proposed framework consists of three main components: graph augmentation, graph representation learning, and graph contrastive learning. The graph augmentation module employs an SGN-based strategy to generate subgraph networks in an edge-to-node fashion, capturing high-order interaction information between substructures. These SGNs serve as augmented views, where original and augmented views with consistent origins are regarded as positive samples, and those with inconsistent origins are regarded as negative samples. In the graph representation learning module, independent encoders are used for different order SGNs to learn graph topology and attribute features, encoding node representations. The node representations are then converted into graph representations using a readout function. A shared projection head projects the representations into a more rigid latent space. The graph contrastive learning module aims to maximize the similarity between positive samples and minimize the similarity between negative samples. A fused multi-order contrastive objective function is proposed to approach multi-order subgraph network representations simultaneously. This function can be understood as a paradigm of global and context contrastive learning, where the graph-level representation of SGNs contains context information from the original graph in addition to global graph information. Comprehensive experiments on multiple benchmark datasets from different domains demonstrate the effectiveness of SGNCL compared to classical and state-of-the-art contrastive learning methods in both unsupervised learning and transfer learning settings. The results show that SGNCL achieves competitive or better performance on all datasets in unsupervised learning settings and the best average gain of 6.9% in transfer learning compared to the best method. The introduction of subgraph networks in GCL offers a new perspective on the interaction between substructures in graph contrastive learning. This approach not only captures the local structure similarity but also preserves the potential structural information to obtain better augmented graphs for subsequent contrastive learning. The proposed framework for graph representation learning and contrastive learning focuses on molecular graphs and social networks, leveraging a novel graph neural network (GNN) model, SGNCL. The SGN-based graph augmentation process transforms molecular graphs into subgraph networks, enhancing interaction information through edge-to-node mapping, which generates first-order and second-order subgraph networks. A graph encoder, based on graph isomorphism network, GIN, processes these views separately, with similar configurations except for input dimension. The readout function compresses node representations into a graph representation, which is then mapped into a latent space using a nonlinear transformation, named shared projection, enforcing mutual information between views. The contrastive objective function, NT-ZENT, compares projection vectors from the original graph and augmented views, encouraging graph representations to be consistent with their augmentation projections. In the unsupervised learning setting, SGNCL is compared with 5 graph contrastive learning methods, showcasing its excellent graph classification performance in most datasets. The model's effectiveness is attributed to its ability to mine interactive information between topological structures. In the transfer learning setting, SGNCL is pre-trained on a general dataset and fine-tuned on specific chemical molecule prediction tasks, achieving the best performance on 4 out of 8 datasets. An ablation study demonstrates the effectiveness of the contrastive objective function for fusing multi-order SGNs. Visualization analysis of the graph-level representations and subgraph networks further supports the model's ability to capture relevant information. Hyperparameter sensitivity analysis shows that the model's performance is maximized when the emphasis on first-order and second-order SGNs is equal. Overall, The SGNCL model offers a promising approach for graph classification tasks by leveraging the interaction information between graph topologies. The authors introduce a novel approach to graph contrastive learning, leveraging subgraph networks, SGNs, as augmented views for enhancing the transferability and generalization of graph neural networks. They propose a new framework that utilizes SGNs to mine the latent interactive information in the original graph topology, leading to better performance in graph classification tasks. The paper discusses various techniques for generating SGNs, including node-to-node, node-edge, and edge-edge interactions, and proposes a novel contrastive objective function for fusing multi-order SGNs. A visualization analysis on the MUTAG dataset is presented, showcasing the similarity between graph-level representations in Figure 4. The sensitivity of the approach with respect to the hyperparameter Q is investigated in Figure 5, highlighting the importance of selecting an optimal value for Q to achieve good performance. A heat map-based visualization in Figure 6 illustrates the similarity between instance groups with labels 1 and 0, utilizing dark colors to signify high similarity between Zori and ZSGN, and light colors to represent low similarity. The results are presented for three variants of their approach: SGNCL, SGNCL-V2, and SGNCL-FU. Figure 6 demonstrates the dynamic adjustment of similarity between views in the method, illustrating how the similarity between Zori and ZSGN1, Zori and ZSGN2, and Zori and both ZSGN1 and ZSGN2 evolves during the training process. This highlights the adaptability of the author's approach. The experimental results demonstrate that considering interaction information as a contrastive item is beneficial for achieving better graph representations. The paper concludes with a discussion on future work, including the improvement of the association framework of SGN and GCL. A comprehensive survey of existing research in the field of graph neural networks, contrastive learning, and subgraph networks is also provided, emphasizing the importance of graph augmentation techniques and contrastive learning in enhancing the quality of graph representations.